Hi, I'd like to do a practice problem with you, problem 1.35 in the back of chapter 1. And 1.35, if you can see here, says draw structures for all constitutional isomers with the following molecular formulas. And they give us some examples. So we're going to choose A first, which is C6H14. All right, so the first thing we need to know for this question is what is a constitutional isomer? And a constitutional isomer or two chemicals can be considered constitutional isomers if they have the same molecular formula but different molecular connectivity. What does that mean exactly? That means C6H14 as a formula can actually have different structures depending on which carbons are attached to which other carbons. Okay, so one other thing that we need to know about how to make constitutional isomers is, are there any rings or double bonds present in the molecule? And unfortunately, your book puts in problems like this way before they teach it to you. So what we're going to do is we're going to jump over to my notebook, and I'm going to show you how to calculate or how to know for sure whether you have any rings or double bonds in the molecular structure that you're trying to draw from a molecular formula. In chapter 14.16, you'll find a description of how to calculate what's called a hydrogen deficiency index. The hydrogen deficiency index tells you if there are rings or double bonds present in a molecule, because if a molecule is termed hydrogen deficient, we will know it from this formula. And hydrogen deficiency happens whenever a carbon has, or whenever a molecule, such as whenever a molecule has less than 2n plus 2 hydrogens. So let me explain what that means. Looking at the notebook here, let's say we have a molecule C2H6. There are 2 carbons and 6 hydrogens. A molecule is considered fully saturated, meaning not deficient, if the number of hydrogens is equal to 2 times the carbon plus 2. So that means if C2H6 is fully saturated and not deficient, it will have 2 times 2 plus 2, which is 4 plus 2, which is equal to 6. So we do in fact have 6 hydrogens with C2H6, so that molecule is not hydrogen deficient. And that's kind of what the hydrogen deficiency index is telling you. If we now put in C2H6 into this formula, what we have for the hydrogen deficiency index is, so we're just going to do this right here since it's a little easier, and I'll do it in red. So HDI is equal to 1/2 times 2 times the carbons plus 2 minus the hydrogens. Okay, so let's move this over so we don't run out of room. There we go. There we are. Okay, so then moving forward with that, we have this equal to 1/2 times 2 times 2, because we're working with C2H6, plus 2 minus 6. So that is then equal to 1/2 times 4 plus 2 minus 6, which is equal to 1/2 of 0, which is equal to 0. So C2H6 has an HDI of 0, meaning it has no double bonds and no rings. Okay, So now you can tell if a molecule is fully saturated, meaning no double bonds and no rings, if its HDI equals 0. If the HDI equals 1, then you can have a ring or one double bond. If the HDI equals 2, you can have a ring and a double bond, or maybe two double bonds, or maybe two rings. Okay, so let's look at A again from the homework, or not from the homework, from practice problem 1.35. And A says, we're looking at the constitutional isomers for C6H14. Okay, so using our HDI formula, we have HDI is equal to 1/2 times 2 times the number of carbons plus 2 minus the nitrogens minus hydrogens. Is that right? Plus nitrogens minus hydrogens. Sorry about that. Plus nitrogens minus hydrogens minus halogens. Halogens are like chlorine, bromine, fluorine, etc. This simplifies a little bit because now we have 1/2 times 2 times 6, the carbons, plus 2, and we don't have any nitrogens, we don't have any halogens, so it'd be minus 14. Okay, now this simplifies further to 1/2 of 12 plus 2 minus 14, which is equal to 1/2 of 0, which is equal to 0. So this molecule is fully saturated, meaning we don't have to worry about any double bonds or rings. Okay, so now what we need to do is start drawing the constitutional isomers of this molecule. So first, we'll draw a molecule where all of the 6 carbons are arranged in a single line. There we have it. There we go. Okay, these are all H's. Sorry for my bad handwriting, but it gets very tedious to write all these in. So I try to take shortcuts, and that's what it gets me. Okay, there's one constitutional isomer, C6H14. You can verify the number for yourself if you want. Next, what I recommend doing is taking one of the carbons, the end carbon, and attaching it in a different place. So let's take that carbon and let's attach it to this carbon instead. Please note, you cannot attach it to this one. That's impossible because if you do, you'll end up with the same thing. It's already attached to that carbon. Okay. Great. Uh-oh, Murray's getting upset, the dog. You'll meet Murray at some point, I hope. Okay, so then we're attaching that carbon to a new place. So let's do that. So carbon, 2, 3, 4, 5. There we go. Great. These are all hydrogens again. It gets very tedious drawing them in. I'm excited for us to learn how to skip drawing in all these hydrogens, which we will cover. Okay. Next, we need to change where that position was. So remember, that's where this one came from. We'll circle in orange so we remember. Next, let's take that same carbon and we'll attach it to this one. Okay. So I'll just draw this one in purple so we keep them straight. Carbon, carbon, 1, 2, 3, 4, 5 again, except now the carbon is here in the middle. Okay, great. And next, we just need to decide if that's all of the constitutional isomers. Because if we take the same carbon and we then try to move it to the next place there, that will actually be the same molecule that we drew in orange. Because if you can flip a molecule and make it the same thing, then it's the same molecule. So because we can't do that, now we have to decide what else we can do. Well, we could instead take 2 carbons, I think. Yeah, we could take this carbon, and we can move them onto this carbon and this one. Okay, do you follow what I'm about to do? Here we go. We could make 1, 2, 3, 4, and attach the 2 carbons here. It's important to note it doesn't matter which side, up and down at this point, that we're drawing these carbons. Okay, so that leaves us with 4 constitutional isomers. And now we're only missing one of them, I believe. And so the only other real option we have is to, I think, take those same 2 carbons, this one and this one, and let's add them to the same one now. So I'm just playing around with these, you know, trying to put these in different places to make new compounds. And I've been doing this a long time, so this is why I can just know kind of what they look like. But you can also find these structures for yourself simply by drawing out different combinations and seeing for yourself, are they the same molecule, and do you get the same molecular formula of C6H14. So these are all 5 of the all of the constitutional isomers that we found from C6H14. And you can verify using the Student Solutions Manual provided to you by the First Day program that these are in fact the 5 that you should be drawing. Typically the ones on a test won't be so tedious, but these do take a little bit of time to solve. So hopefully you found this helpful and interesting, and thanks for being here with me today.